welcome to the final day of CHES. So this session is on side channel analysis of software implementations. We've got 3 papers today, and the first one is called Trace Copilot, and it'll be presented by Shipei Shu.
Hello. Okay, thank you. Thanks for having me here. And today I'm going to share our research work on how to automatically locating cryptographic operations in side channel traces with the help of binary firmware. Okay. So our main topic, physical side channel attacks against those embedded devices. I assume most people here are very familiar with this topic, so I'll skip those basics. Okay, so what's the problem? When we are conducting some real-world attacks against some embedded device like a camera or some controller, we find that ourselves spend most of the time in pre-processing the traces, but like locating the CO position or aligning them, etc. So we ask ourselves how to locate this COC in the raw trace more efficiently. And when we look at the papers, most of them adopt laboratory settings, because they focus on the theoretical feasibility. So most of the time they will add manual triggers like before or after the call to cryptograph function. So for fast evaluation, right? But in the real world settings, you do not have such source code, maybe precise triggers. So locating and aligning those COs from a long and noisy trace could be a very labor work. So we need more automated methods to accelerate this process. And there are actually already some research works that directly or indirectly supports automatically locating the COs. For example, I assume you know the deep learning-based end-to-end side channel attacks. So they didn't require you to explicitly locating the COs, but only require you make sure the COs are locating within your input trace for the model. However, this approach is of course limited by the model input size. So you still have to first narrow your input trace down to the input down to the some range and make sure it contains the target COs, right? And another interesting approach is developed proposed in CHES 2022 called semi-lock, and it exploits the repetitive patterns of the cryptographic functions. Like there are many runs in cryptographic algorithm, and maybe they are quite similar. So you can scan the trace and find those repeating patterns. However, this approach also requires you know the some prior knowledge about the target. For example, you know how many runs here and how long will a run take. So what can we do now? First, we find that if you really do not know nothing about the target, it's inevitably you have to spend the labor work at guessing or searching the raw trace for you manually. And the second observation is that we found that in the real world settings, sometimes we may obtain the binary firmware of the targets. For example, dumping the flash or eMMC chips, or some like hardware wallet vendors, they will publish their firmware building for the transparency for their users. Make sure there are no backdoors in it. And those binary firmware, they may not contain the secret key, but they may contain the software implementation about the algorithm. So we propose a question that can we use this information from binaries to accelerate locating the CEOs on the side channel traces? Because if it's software implemented, you got the binary, means you got almost every details about this implementation. And our motivation is quite simple, because in a software implementation, the program instruction flows actually has some correspondence to the CEO's target, CEO's side channel trees. If we can find a way to build a mapping between these two kinds of information, maybe we can locate the CEO in the trees by locating the CEO in the binary, right? So how to map the program flow to the side channel trees? We proposed a scheme can be broken into like 3 steps. So the first one, we start by parsing and disassemble and analysis the binary firmware, and we select some interesting anchoring instructions. And the next step, we perform binary instrumentation, which actually modify the target binary to inject some synchronization signals, like triggers or some UART logs. And this next step, we run the modified firmware on the target devices, like a profiling device, to gain the triggers or some other information, and then we using this information to segment and annotate the trace. Yeah. So the first step, how do we find the suitable anchoring instruction? The important point here is granularity, because like you monitor each function call and return, then you will not have a good segmentation of the target cryptography operation. One function may contain many operations here and may contain many rounds. And if we make it too fine for like every single instruction, there will be much more overhead and noise in our results. Okay, so after balancing the trade-offs, we decide to tracking at the basic blocks level in the control flow graph, like it almost always corresponding to a specific step in the cryptographic algorithm. And for ARM Cortex M architecture, it means we have to track the instruction like the branch related. And the next step, how we perform the binary instrumentation, like in x86, we call it hooking or something else. But in the bare metal embedded software firmware, it's not that easy to perform those hooking. So we start by replace the target branch instruction with like illegal instruction, like undefined ones or something will cause the exception. And then the processor will enter a so-called exception handling process. And before we flash the firmware, we modify the exception handler and make it point to our own code, so we can hijack the control flow to our own code. And in here, like the origin blocks, we can do our like pulling the trigger or printing some UART logs. Of course, there will be many corner cases and fixes to make sure the overwritten instructions still executed correctly. So, but it's beyond our paper, and we just use previously developed a tool, actually written by me. Yeah, we use this paper framework to handle all these corner cases. Okay. So for now, we can when the target device executes to this instruction, we will have a binary level trigger we injected. And but the trigger signal, maybe it cannot tell us which instruction varies, right? Because it's only a mid-level change. So we still have to collect which basic blocks are firing it. So we build another modified firmware, like we set a hardware breakpoint here, like in the hooking code, and use a GDB script and a debugger to automatically collecting the stopped addresses. So after this step, we will get two lists. One list, one list is the timestamps of the triggers, and then the other one is PC addresses that of the executed basic blocks. So we can map those two lists one to one, and then we will know at a specific time stamp which basic blocks is executing. So we can segment the target raw trace and annotate it. An additional step may be performed code is to eliminate the noise and from the raw trace, because you know we inject more code than the original cryptographic function, right? So we can use the oscilloscope to measure the code we inject, take how long in this process and its delay with the triggers, so we can remove them from the segmented traces we just produced. And so now we build a mapping between the execution flows of the basic blocks and the side channel traces. But actually, there are many basic blocks in firmware. We still need to distinguish the cryptographic ones from others, and the other, and and then we also need to perform it in a profile attack way. Like we need to locate CO for unmodified target. So this process is also roughly broken into three steps. Okay, the first one is we locate the cryptographic function, and then inside the function we focus on which blocks, like the loop body, that corresponding directly to the cryptographic operation, and after that we we select the segments on the traces that corresponding to them, and we build a template to perform template matching on our device that we cannot control. So for the function level detection, there is actually some previous work proposed by like software security researchers. So we just reuse them. And but the function level detection is actually not enough for side channel analysis, because maybe for AES you want to pinpoint specific rounds, right? So we need to find a more finer grained operations. So in here we decide to use loop body as a basic CO unit, because it constitutes most of the cryptographic operations we know, and it's relatively easy to determine the firmware. And another issue arises from the setting we just listed is how we identify the CO-related loops from others. Here we just adopt two strategies. One is heuristic filtering. You can use some basic rules to filter out those ones that obviously not cryptographic operation, like memory copy, memory set. And another one is we exploiting the timing characteristics. For example, in the right figure, it's ECDSE signing process we collected from embed TLS, and you will see the most important cryptographic operation loops will take the most of the execution time, and it will have distinguished characteristics, so we can use this information to filter them. And the next step is now we know which loop corresponding to the cryptographic operations, right? But we want a more accurate slice in the raw traces, so we need to find the exact instruction control the loops, like split one round from another. So we basically find the package in the nature loops, which is a conception in the compiler design. So by selecting this instruction, we can precisely cut out different rounds. And the final step is that how we locate the COs from a trace which is collected from targets that we cannot modify its firmware. We actually here using a scheme like a profiling attack. So we first build those templates in a controllable device, and we use the build template to do template matching in for the target raw trace. So here we choose a frequency domain feature template, which is also quite common in the side channel analysis. So for the unmodified target raw trace, our template will yield like more higher similarity score at the target location. Yeah, and the evaluation part, we implement our proposed firmware analysis and instrumentation framework in Python and with the help of Ghidra framework. And the evaluation basic setting, we use EM set channel trace using a longer probe and oscilloscope. And devices under test are selected from Cortex-M devices. And the first experiment, we trying to hide a small AES call in a long and very noisy trace. You can see from the upper left figure, you can hardly locate it with the human eyes, right? It will cost you many human labor work. And using our method, you can scan those raw trace and find where the crypto operations are. And in the second experiment, in second evaluation, we trying to we tried a interesting test that our approach can actually ignore the random delay count measures between the rounds of the AS implementation. So you can see there is a random delay between the different rounds, but our template matching still works because it actually can ignore those other loops as we just discussed. And for the third experiment, we trying to locate more complex COs. As we know, the previous work only focused on simple ones like ES or other ones. And for the ECC ones, here in a real implementation in embedded TLS, you can see at first our template matching is not quite work, but a deeper analysis shows that it is very interesting that the features of this CO is mostly located at high or mid frequency band. So we, but in the older evaluation, we only use the low band pass features. So we moved to a band pass filter, and we extract those new features as template, and we can get the correct results as shown in the right figure. And the final experiment, we trying to locate CO yield from real-world closed-sourced cryptography library, which is made by ST. Yeah, it's an official crypto lib by them and used in their secure boot implementation. So we stack the AES as the target CO, and the results show our implementation can easily detect where it is. Okay, in summary, our contributions, we build a scheme that bridges binary code with physical side channel traces, and we write a framework to automatically utilize the binary information for CO locating. And in future works, maybe we can use the information in the other direction, like use side channel information to assist binary analysis, or we can extend the current implementation to support more architecture, but most of the work will focus on the binary instrumentation framework. Yeah. And there are some references in these slides. And okay, that's my talk. And you can check our paper and our open source code for more details if you are interested. And yeah, that's all. Now I'm happy to take some questions, maybe. Thank you.
Hi, thanks
Hi.
for your cool, oh, sorry. Did I go too fast? Thanks for your cool talk.
Thank
Did you
you.
use the same instance of the chip for the profiling phase and the attack phase?
It's actually two different instances, but the same, exactly same model.
Oh,
Yeah,
okay,
like
cool.
in the profiling attack across device ones.
Right, and the second question is
Yeah.
the secure boot code that you figured out, is that open now, or did you publish that?
What's the open means?
Or like, yeah, is it available online now?
The secure boot code is open sourced by actually ST.
Oh, I see, sorry,
Yeah.
my mistake.
Yeah.
Thanks.
Okay, thank you.
Thanks for your great talk. And
Thank
I
you.
want to ask, why did you use the binary instrumentation rather than the debugger breakpoints?
Okay, that's a very good question. In short, the debug breakpoints like in the embedded device like Cortex-M, there are two kinds of breakpoints. One of them, one is software ones, like you use GTAG or GDB debugger to attach it. It will replace the targeted instruction to someone or in the memory, and like the int3 in the x86, and then when the device run into this instruction, it will raise it will find the external debugger to take over. So, but this process is very time consuming. You know, the overhead between your PC and the target device, so it will disrupt the side channel features in the traces. And another one is like hardware breakpoints, but it can be, actually our implementation is quite similar to the hardware breakpoints, but the hardware breakpoints are very limited on those devices, maybe 4 or 6 at most, in most devices I ever know. Yeah.
Okay,
Is
thanks.
that clear?
Thanks.
Okay,
Yeah.
thank you.
Thanks for your talk. Another
you.
small question is that is your tool capable of handling maybe obfuscated firmwares?
Excuse me, can you repeat?
Is your tool can your tool handle the obfuscated firmwares?
You mean obfuscated, like
Yeah,
control flow flattening, those ones?
Yes.
The shorter answer is no, yeah. But luckily for embedded devices like those Cortex-M ones, it's very rare to see such heavy obfuscation, because there will be lots of runtime and space overhead. Yeah, but since we depending on the relation between the binary structure and the cryptographic operation, so the obfuscation, of course, we cannot handle right now. Yeah.
Okay, thank you.
Yeah, very good question. Thank you.
Another question is, your work is depend on locating and marking the branch instructions.
Yeah.
Maybe loops in
Yes.
the code. So, what if there is loop unrolling?
Yeah, I know your point. Because actually, there is one statement in my slides and in our paper, like, yeah, loop unrolling is not considered right now, but in our experience, like the embed TLS library, even you build it with the default options on those Cortex-M devices, it will not perform the loop unrolling because, for these devices, it's memory constrained. So if you unloop the loop, the binary size will be bigger. But those devices, they prefer optimize the size because the constrained environment. Yeah.
Yes. Oh, okay. Thank you.
So I have one question. Do you plan to extend this work to devices which you do not have the source code?
Actually, we already extended to Cortex-A, some, running the Linux ones, the more advanced ones, because we found it actually more easier to perform binary instrumentation at their firmware, like in the U-boot or ATF. Yeah, we are making it happen, and a paper about that is going to be published maybe recently. Yeah.
Okay, let's thank the speaker.
Okay, thank you.
The next talk is called on the paper called Mid P Square, and the speaker is Throben Moss.
Okay. Thank you for the nice introduction. Yes, I'm talking about Mid P Square, which is a masking-friendly tweakable block cipher. And this is a joint work with Brieux, Lorenzo, Pierrick, François-Xavier, and Matthias. So this is the last day of CHES. I guess you all have heard plenty of introductions into side channel attacks, side channel countermeasures, and in particular masking. So I'm not going to repeat all of that, but you might have heard a bit less about the specificities of masking in prime order fields. So this is what this is about, and this is like a timeline of all the works that we are aware of that either explicitly study or exploit the advantages that masking over prime fields provides. And it all started with this TCC 2016 work by Dembowski et al., which showed that to get optimal amplification of the noise, which is like the core property, how masking provides security, that to achieve this, you have to work over groups of prime order. So whenever you have a composite order, you cannot achieve this because there will always be non-trivial subgroups, and you have leakage functions that take this security amplification away from you. So this paper, like I guess many TCC papers, has been ignored by the practitioners for about a decade. And then we kind of started to pick it up at Eurocrypt 2023. With the first work that was a bit more practically oriented, and since then we have seen a bunch of papers on this topic at CHES, at Eurocrypt, at AsiaCrypt, looking at different properties that masking over prime fields can provide, both against side channel and against fault attacks, and then we have a few dedicated constructions to leverage these advantages. So to summarize, these works generally agree that in presence of strong physical adversaries, prime field masking gives you some advantage over binary field masking. And strong in this context means low noise attackers for side channel attacks and high precision for fault injection attacks. Now to leverage these nice properties that we can get theoretically best in practice, we kind of require new cryptographic primitives because the ones we are typically using are at best partially, at worst not at all compatible with this type of masking. So for this purpose at Eurocrypt 2024, last year, we introduced the FISA for prime masking family of tweakable block ciphers. And there are now two concrete instances of this family of TBCs. The first one is small p square from last year, which is hardware oriented and uses a small prime, therefore the name. and mid-p-square, which we propose in this work, which is software-oriented and uses a mid-sized prime. Now, to quickly recall this family of tweakable block ciphers, how it looks like. So the structure is based on the Tweaky framework and an LED-like design. So you have versions with like multiple sizes of the tweak. On the left side, you have no tweak, so just a regular block cipher. On the middle, you have tweak size same as key size. On the right side, you have the tweak size twice the key size. And LED-like design means between each tweaky addition, we actually execute the round function multiple times so that we get stronger properties between each tweak addition. The round functions themselves are defined as like a type 2 generalized Feistel to obtain like efficient inverses, and these instances are defined by two parameters, B and C. B is the number of branches and C is the number of field elements per branch. So on the left side you see you have two branches and two field elements per branch going into the F function. And then in the middle there is four elements per branch and two branches, so also four elements going into the F function. The F function itself is defined as a type 3 generalized Feistel. So like two power maps as type 3 generalized Feistel, one at the beginning, one at the end, with like an MDS matrix multiplication in the middle. And the goal is to have this bijectivity and full nonlinear diffusion. And you can choose the MDS matrix and like the power map depending on your implementation constraints. Now this is the instance that we have used so far for hardware efficiency that we proposed last year. It uses the prime 2 to the 7 minus 1, so the Mersenne prime 127. B and C are both 4, so you have 4 times 4 elements of 7 bits, which gives you a 112-bit state. The tweak size is flexible, either 0, 112, or 224. And at the bottom you can see the F function, which uses like the square, which is non-bijective, but because we apply it in a Feistel manner, we can use it and still achieve bijectivity with the MDS matrix in the middle. Now, what are like the disadvantages of this design? Why do we even need like another one or a new one? And the thing is, this design is really only nice in hardware, or maybe also on like 8-bit microcontrollers, but these are not like used a lot anymore. So it's poorly suited for efficient software implementations on modern devices. Why is that? Because the individual bits in my field elements, they are not independent with respect to field arithmetic, like you would have for Boolean masking, for example, or like binary operations. And therefore you cannot do bit slicing, which takes like a lot of efficiency away because you cannot exhaust the register width properly. And you only fill like a small part of the registers, which is, leads to quite inefficient implementations. The second, maybe even more drastic problem is that it does not maximize the security advantages that you can get from prime field masking, because according to theory that has been established in the papers that I showed in the beginning, larger prime moduli give me like significantly stronger resistance against side channel and fault attacks. This is also part of what we want to evaluate in this work. And for this, I'm quickly recapping a result from the Eurocrypt 2023 work, just showing the mutual information over the noise variance, so mutual information on the y-axis, noise variance on the x-axis, and low mutual information means high security, high mutual information means low security. We can see that from the left, 3-bit words to the right, 13-bit words, the mutual information is like drastically reduced on the log scale, so it's quite significant, which gives us significantly increased security. Similar story for fault attacks, so statistical ineffective fault attacks. That is from a paper from last year's CHES, where we can see on the top CIFAR 1 and on the bottom CIFAR 2 results, where we have the CIFAR success rate over the total number of fault attempts, also on a log scale. And the leftmost graph is always for n equals 5, so 5-bit elements, and the rightmost graph for n equals 19. And we can see that growing the field size gives us significant advantages in security. Then another thing, sometimes we might not have to worry about like low noise. If I have like highly parallel hardware implementations, this might be less of an issue. But for software implementations, this really is problematic. And what we mean when we say noise is not only like the point-wise SNRs that you can see on the top right, but actually in these horizontal attacks, you can combine all the information over the entire trace to get like a probability distribution on your secret that is processed. And the only thing that this slide should show is that from like a 12-bit intermediate value, I can, from a very short computation on it, get up to 11 bits of information. So this is much stronger than even noise-free Hamming weight or noise-free Hamming distance models. So this is our new design. This is mid p-square for software implementations. The parameter b and c are both 2. And the prime we are using is 2 to the 31 minus 1. Also a Mersenne prime for like efficient modular reduction. And this Mersenne prime is like perfectly suited because it allows you to do addition or subtraction in a 32-bit register without any overflow, and then you can do the modular reduction, which is just this addition trick. And otherwise, there's the same parameters. You can see that the instance is much simpler than the one for software because we just have less elements to mix, and we only have 2 squarings to perform in the F function. So it's very neat and compact. The main differences, so there's like a table, maybe let's focus on the security. So the security claim for small p-square is 112 bits. For mid p-square, it's 120 bits. And the number of rounds for like the version with key size equals to tweak size, we have the same number of rounds, while for the non-tweaked version, small p-square has less rounds, and for the double tweaked version, mid p-square has less rounds. Now, one important aspect is when I have now fewer words over a larger field, statistical cryptanalysis is usually not dominating anymore, but I have to worry about algebraic attacks. So I need to look at Grübner basis attacks, interpolation attacks, linearization attacks, all this kind of stuff. And then, since like very few tweakable symmetric designs exist in this sphere, there's not much research at all yet on related tweak algebraic attacks. So we know related tweak statistical attacks. We don't really know related tweak algebraic attacks. So we kind of went like the careful route and designed like a very algebraically strong tweak schedule to like, yeah, future-proof the design against advances in this field. And for this, we have designed this tweak schedule. So like, it has 3 operations. One is basically shift rows. One is basically mix columns. The important operation is this psi operation, where we get like a very strong nonlinear function by exploiting that bit manipulations give me something very strong in the prime field. So we just shift the field element 1 bit to the right, XOR it to the original field element, XOR it with a constant, and then we get like a function of maximum degree, so degree over 2 billion, and with like significant number of monomials. Okay, let's look at the performance comparisons. So we compare on Cortex M4, which is like a convenient choice because it has a single cycle 32-bit multiplication. So multiplication of 2 32-bit inputs in a single cycle. And we compare to Skinny and our previous design, small p-square, which is not expected to be very performant in software. For Skinny, we have used an arbitrary order masked implementation that exploits this fixed sliced representation. So in bit sliced implementations, usually operations like shift rows are the bottlenecks because they require to reshuffle the bits in a register, which is quite expensive. So if you can avoid this, you would like to do that. And there has been introduced this fixed slice Skinny representation where you basically change your mixed columns and sub-bytes so that you don't have to perform explicitly any shift rows. And this, on an unprotected implementation, this gives you like 2.5 speed up while you double the code size because you have like more different operations. So in this comparison, we can see like green is best, yellow is middle, and red is worst. Small p square is like consistently the worst, and it gets like much worse at the higher orders. So we have like from 1 share, so unprotected, to 32 shares, and we have numbers including the randomness generation and excluding the randomness generation. For randomness generation, we have used the on-chip TRNG. And mid-p square, our new design, is actually able to outperform skinny and small p square in almost all cases, except for like some special cases at d equals 8, where skinny is slightly faster. Regarding the code size, it looks even much better. I mean, bit-sliced implementations generally have a larger code size. And then a fixed slice implementation even doubles this code size. So skinny has a larger code size, up to even like more than an order of magnitude. And mid-p square is still like a few times smaller than small p square. So it's very efficient from an implementation point of view on this target. This is just a slide to show that the code is super compact. So this is like the entire encryption routine for like the tweak 0 version, including the on-the-fly computation of the round constants. And it looks like there are some function calls in the lower part, but those are actually just single-line C macros. So it's really very, very short code, easy to implement. We have all our unprotected and arbitrary order masked implementations of skinny, small p square, and mid p square in this GitHub repository that is linked and with a QR code. There's platform independent and STM32F4 specific code under MIT license. It will also be an artifact. It's not yet published because there was a submission to the last issue of CHES. So you have to wait for that, but it will contain the same content as is on the GitHub. So finally, like the side channel security comparison. What we see here in the plots is like on the y-axis the averaged key rank after I performed an attack, over like on the x-axis the number of attack traces in log scale. And then the different colors are graphs for like different numbers of shares. 2 shares, 3 shares, and 4 shares. And we can see that for a skinny, we can still break like a 4-share implementation with like a fourth order attack at about like a few thousand traces, significantly less than 10,000 traces, which is quite powerful. And for mid-p square, we actually have to compare to this part on the bottom right. Now the problem is we can only extrapolate this result because evaluating these profiled horizontal attacks over this field size is like prohibitive. So really computing this entire graph would have taken us like multiple years on our strongest computation server. And even then you have the problem that you have so many classes in your profiles, if you profile like the entire intermediate values, that they will not be represented until you have like a prohibitively large number of traces. So it's super hard to perform these attacks in practice. So what we did is just reducing the size of the prime and seeing like which of these we can do and see how the security develops over them. So we start with like 2 to the 7 7-bit elements, and 2 to the 13 and 2 to the 19. And it's visible that like the security, especially for 4 shares, increases like significantly from like 10 to the 3 to 10 to the 4 to almost 10 to the 6. And that would be extrapolated. So the distance between this one and this one is half as much as from this one to this one. So this is where the extrapolation comes from that we see here. So even if you don't trust our extrapolation, I think it's hard to deny that the real attack will at least require this many traces, and this already gives me like a 3 orders of magnitude advantage in attack complexity over like the comparative skinny implementation. With respect to transitional leakages, we also have an advantage. So at the very top, there is a graph that shows the mutual information between just the XOR between 2 shares in a 2-share implementation. So how much does the Hamming distance between 2 shares provide me as information? And you can see that for Boolean masking, this goes up because it's just a Hamming distance information and it increases in the field size. For additive prime field masking, it's actually going down. So not only relatively in relation to the field size, but also the absolute value is going down. So there's like significantly less information, and out of 30 bits, you leak maybe like 0.3. Then we have evaluated like 2-share implementations without any hardening, without any measures to get rid of transitional leakages. And there with Skinny, we see that there's like very significant first and second order leakage. For mid-p-square, there's also first and second order leakage over the T threshold, but it's significantly less. So that kind of confirms our information theoretic analysis. Now, if you want to get rid of that and you want to have like clean t-tests with only 2 shares, there are basically 3 things you can do. Then are only 2 things, because one of the things is you increase the number of shares. The other one is you use like a more complex encoding, like in a product or code-based, that would give you a better behavior against transitional leakages. And the third one is like manual hardening or like automated hardening on an assembly basis. Yes. Then, in summary, mid-p-square is a novel TBC that's optimized for prime field masking on 32-bit software platforms. I believe it's easy to implement. It definitely uses little memory, leads to short code, fast compilation times, and small binaries, even at very high security orders. It's significantly faster and smaller than small p-square on the Cortex-M4. It's slightly faster, but much smaller than fixed sliced Skinny on Cortex-M4. In hardware, we don't have any results of that in the paper, but we have implemented that by now. We're about like 2 times larger than small p-square or Skinny. So hardware efficiency is not the very best, but I think for the security gains that we see in practice, this can be even in hardware kind of interesting. And for future work, we would like to, because I mean, these designs are by design kind of very compatible with other more complex masking schemes from like a recombination function point of view, like inner product masking, code-based masking, multiplicative masking, and they could even lead to better efficiency security trade-offs. That's something we want to explore. And with that, I conclude my talk, and I'm happy to take any questions.
So are there any questions?
Hi, nice talk, thanks. In between you had once some Boolean operations. These were only on values you don't have to mask, or did I misunderstand? So there was this XOR operations and shifts.
Yeah, okay, sorry, I kind of forgot to say that. So this is a tweak schedule, and here we use like XORs and shifts because we don't want to mask it. The tweak is usually considered public.
So no problem, okay.
Yes. I mean, this masking this psi function would anyway be a complete nightmare. We cannot even write down the polynomial that it computes. So this we can only use in the tweak schedule and never in the round function.
Okay, and this value stays always smaller than your prime, as it's between 0 and prime minus 1. Okay.
Yes.
I don't see. Okay, thanks.
It's bijective and always gives a field element.
Okay.
So I have one question.
Yes.
Could you comment on the ease or difficulty in ensuring that your the source code is the code is essentially constant time?
So I think all the core operations that we use are kind of anyway constant time, especially on this Cortex M4. But once you switch compilers and targets, of course the compiler can ruin the constant time properties. So I think you would need to use the same precautions that you would use with any other constant time checking for, yeah.
Okay, one more question. So this is targeted for 32-bit platforms, right?
Yes.
What would you do about, you have to use an 8-bit or a 16-bit microcontroller? So what would you say about the portability of this algorithm?
So this algorithm I would not want to implement on anything smaller than 32-bit operand size. I would choose like the other design then, because I think then you have like multi-precision arithmetic and that makes everything like significantly slower.
Another question. Did you implement it on Cortex M0 where you have only this 32-bit multiplication where the top is cut off?
We did not, in part because like the memory is already not sufficient to fit our competitor Skinny on it. So no, we did not implement it, but there you have like only 16-bit multiplications in one cycle, right? So you also have to use multi-precision arithmetic. So you probably have to call it 4 times at least. Yeah, no, we did not test this.
Okay, thanks.
Let's thank Throben again. So the final paper in this session is called Malleek, and the speaker is Fan Huang. So he's not present here, so we have a video for it.
To attack the stack-optimized Kyber implementation on Cortex M4. A joint work with Xiaoling Duan, Chen Chonghu, Meng Cezhen, and Honggang Hu. Our presentation starts from the background. Then we will introduce our proposed model and attacks. Finally, we will discuss our experimental results and make a conclusion. Quantum computation threatens today's public key cryptography, accelerating the development of post-quantum cryptography. Last year, NIST dropped a new standard, FIPS 203, a modular lattice-based KEM standard. This standard is built on Crystal's Kyber, whose security assumption is the harness of the modular LWE problem. In modular lattice-based cryptography, polynomial multiplication is a core operation. NTT, including its inverse and pointwise multiplication, are used to implement the multiplication of polynomials in Kyber. Notably, Kyber employs an incomplete NTT, which skips the last layer and leads to the polynomial multiplications of degree 1. Here, we refer the degree 1 polynomial multiplications as pair point-wise multiplication, which is the target of our work. PQM4 is a reference framework for benchmarking implementations of PQC algorithms for ARM Cortex-M4 devices. It provides 2 optimized implementations for Kyber. Here, these 2 figures show the code of the pair point-wise multiplications in 2 implementations. The speed-optimized implementation employs a lazy reduction strategy and thus need to store instructions for each result coefficient. The stack-optimized one reduces the number of memory operations by saving 2 result coefficients with 1 single instruction. Since polynomial multiplication is a core operation in Kyber, MiniWorks targets NTT, or the pair point-wise multiplications. They commonly use the Hamming weight or noisy Hamming weight model to calculate the power consumption leaked by the secret data. Most of these studies opt for memory operations, assuming that they yield great signal-to-noise ratios in power leakage than register updates or combinational logic. The standard optimized Kyber stores a pair of result coefficients at once, indicating that attackers who want to exploit store instruction leakage need to predict a pair of secret coefficients at once. This results in a first-order attack with a complexity of big O Q squared n over 2, and a second-order attack with a complexity of big O Q to the power of 4 n over 2. Now, one question arises. Can we predict the secret coefficients one by one and reduce the complexity of the attack? Our answer is exploiting multiply instruction leakage. In this work, we propose a novel linear regression-based cycle-level leakage model. Based on the model, we present two profiled attacks. They leverage known ciphertext and the chosen ciphertext methods. And the second one can also be extended to the masked implementation. Our first-order attacks achieve a success rate above 97% using only a few dozen traces. The second-order attack targets the masked implementation with a success rate around 96%, requiring 201 traces. Our experiment focused on the macro double base mal from bytes ASM. We utilized the chip whisper platform with the STM32F303 target. In order to reflect a real-world scenario, we use two devices, one for profiling and one for attacking. We use picoscope 5444B to record the signal with a sampling rate 250 megasamples per second, with 10-bit resolution. In terms of trace compression, we sub all sampling points within each cycle to calculate the cycle level power consumption. In 2017, McCann et al. Proposed a Greenberg's instruction level leakage model based on linear regression. This model characterized the power leakage of instructions from ARM Cortex-M0 and M4 devices. In the model, the predicted leakage Y prime is modeled via the least squares estimation, where OI and O tilde I are register level variables. Big OI and big TOI are explanatory variable groups. We expand this leakage model by ending the power leakage from registers and combinational logic over the entire clock cycle. First of all, we discuss the power consumption of Cortex-M4 during a single clock cycle. Left figures show the pipeline architecture of the device and the state changes during a clock cycle. For each instruction, operands are transferred from general purpose registers to pipeline registers. Then processed in function unit, here marked in DSP extension. Then the results read back to the destination register. Since EX and RS stage may process secret data, we will pay more attention to the power consumption during these two stages. In the left bottom figure, cycle J denotes the current clock cycle, and inst I is the current instruction. So, in the current clock cycle, pipeline registers update operands from the current instruction. The general purpose registers store the result of the previous instruction, and the functional unit executes the current instruction. Based on the previous discussion, we expanded the model proposed by McCann et al. And gave our basic leakage model. The number of operands in the model changes from 2 to 3. R is the result of the previous instruction, and R tilde denotes the prior value in the destination register of the previous instruction. Explanatory variables consist of big R, TR, DM, TDM, and so on, where big R represents the vector of bits from R, TR is the vector of bit transitions in the general purpose register. DM and TDM are two explanatory variable groups related to the combinational logic. To characterize the power leakage in the combinational logic, we need to ascertain the type of mark circuit. After looking into this, we are down to boost volume multiplier, radix 2 boost multiplier, and the radix 4 boost multiplier. Then we focus on the distinct roles played by the multiplicand and the multiplier. For boost volume multiplier, the multiplicand and the multiplier have a similar impact on power consumption, but that's not the case for boost multipliers. For boost multipliers, the operand decoded by boost encoder has a significant effect. For radix 2 boost multiplier, each bit of the decoded operand may generate a negative code to produce a higher power consumption. For radix 4 boost multiplier, the old bit of the decoded operand may generate a negative code to produce a higher power consumption. Our experiments show that different effects from two operands, so it is not a boost volume multiplier, and the decoded operand is the multiplicand, and significant effect from the old bits of the multiplicand, which consistent with the power feature of radix 4 boost multiplier. We employ a classic design of the radix 4 boost multiplier for simulation. As shown in left figure, the intermediate variables include 8 partial products, 8 hot ones, 9 safe variables, and 9 carry variables. Then we transform these intermediate variables into explanatory variable groups of the leakage model. Considering the presence of dual multiply instruction in the target implementation, we need to further refine the leakage model. The instruction SMUADX performs two 16-bit multiplications, as we can see here. Thus, we let the explanatory variable group DM be two parts, DMB and DMT, responds to the bottom and top 16 bits of the multiplicand, so as the corresponding transition variables DDMB and DDMT. Based on our model, we proposed two profiled attacks. The left figure shows our attack methodologies. For non-ciphertext profiled attack, TCPA, the first 4 instructions only related to the secret coefficient SK hat 1. And the following 6 involve both SK hat 1 and SK hat 0. So we utilize the leakage in the first 4 instructions to recover SK hat 1. And then we use the recovered SK hat 1 to recover SK hat 0 based in the following 6 instructions. Here, CT hat 1 is not 0. In chosen ciphertext profiled attack CCPA, we can select the ciphertext. There are 2 cases. CT hat 1 equals 0, and the CT hat 0 equals 0. But when CT hat 1 equals 0, we can see that the first 4 instructions cannot be employed. Thus, we discuss this case. when we set CT has 0 be 0, the dependency between SK has 1 and SK has 0 could be broken. We can independently recover SK has 1 with the first 7 instructions and SK has 0 with the last 2 multiply instructions. The CCPA requires specific ciphertext where CT has 1 is not 0 and CT has 0 equals 0. We offer a straightforward approach to generate polynomials that meet these requirements. Firstly, we initialize a set C, whose elements remain unchanged after applying compressed Q and decompressed Q functions. Next, we generate a ciphertext polynomial CT in normal domain. Let the coefficient C21 be the element in set C, and the other coefficients of CT be zeros. Finally, we apply NTT to CT to get CT hat in NTT domain. Thus, we can see that the old coefficients of CT hat are CT1, which are not 0, and the even coefficients of CT hat are zeros. Now, we talk about the second-order attack. The TCPA is not suitable for the second-order attack because of the dependency of the recovery of SK hat 1 and SK hat 0. The CCPA predicts the secret coefficient shells individually, thus it is opted to target the masking implementation. When predicting a coefficient, we need the loop likelihood values of Q-squared pairs of shells. In these Q-squared pairs of shells, only one pair corresponds to the correct secret coefficient shells. We set a rank threshold to prompt some of the incorrect pairs. We can use the Hamming weight information of the result coefficient pair to filter secret coefficient candidates. Here, R hat 1s and R hat 0s are the correct result coefficient. R hat 1 and R hat 0 are our guess coefficients. The following two conditions should be satisfied, but practically in template text, the Hamming weight guess value with rank 0 is not necessarily the correct value with 100% possibility. So we modify the above conditions in this form by selecting several top-ranked guess values. This can reduce the possibility of erroneous filtering. Now we talk about the experimental results. The pre-processing in our work contains these parts. For trace fragment, the target function consists of multiple macros. For trace alignment, we use cross-correlation. For instructions location, we use SOST. For template generation, we instantiate the leakage models for each multiply instruction, and then to generate the template mean and covariance for each secret coefficient. The table shows the R-squared values of each model with different numbers of trace fragments for profiling. As shown in the table, all R-squared values are above 0.6. As the number of trace fragments increases, R-squared values show an upward trend. We show the results of recovering Hamming weight of the result coefficient pair. For each Hamming weight value, we collect 2,000 trace fragments to generate the template. And we utilize 1,000 trace fragments to evaluate the matching probabilities and rank the candidates accordingly. The above table shows the probability that the correct Hamming weight value falls in the top NHW ranks. The bottom table shows the probability that the correct Hamming weight value is no longer than the maximum value of the top NHW candidate. This table shows the performance of attacks against the unprotected implementation. It should be noticed that condition 2 is only applicable to the recovery of SK hat 0. In the table, the best performance is achieved when NP equals 49,920, NHW equals 6. KCPA and CCPA require 12 and 26 traces for the original text, 12 and 13 traces for the condition 2 augmented text. The table in this page shows the performance of the second order text. We give 3 values of rank threshold. In the table, the best performance is achieved when NP equals 49,920, NHW equals 1, and the rank threshold is set to 512. 259 traces are required for the original tag, 201 traces for the condition 1 augmented tag. Two works target the same or similar implementations as our work. Compared to the work of MWK plus 24, the authors utilize correlation power law analysis to predict the two secret coefficients at once with 200 traces. However, they did not attack the masked implementation, whereas we did. Compared to ABB plus 24, we use a few hundred traces for profiling, and they require millions of traces. Moreover, their attack is conducted on a single device, but we focused on a real-world scenario. We use 2 devices, one for profiling and one for attacking. In sum, this work, we propose a novel leakage model, which contains 3 parts that related to the secret data. Based on the model, we give 2 profiled attacks, KCPA and CCPA, to predict the secret coefficients individually. The complexity of the first-order attacks is big O, Q, N, and the CCPA could also be used to attack the masked implementation with the complexity of big O, Q squared N. That's all. Thanks for your attention.